Okay, welcome to everybody. We are going to have lectures given by Frederik Van Der Veken. He studied as particle physicist and now he works at CERN in the Accelerator division. And so we are going to learn a lot of secrets about how these big machines work and the physics prepared around. Please, Fred, it's up to you.
Okay, I have actually a feedback. I'm gonna mute somewhere. Sorry for that. Okay, I think it's fine now. So, hi everybody, and yeah, welcome. So, first of all, this is actually meant to be some kind of interactive talk. So, whenever you have questions, put them in the comments, and I will do regular stops, and then we can check whatever are the comments, and we can discuss, and I can actually try to answer these kind of things. Okay, so we're going to talk about particle physics. We have big machines, high energies, and tiny particles. Physics at the femtoscale. That's the title of the talk. That is what we're talking about. But of course, then the first thing is, what scale? What is a femtoscale? That's a very important thing, because people always talk about femtoparticles, femtometers, this kind of thing. So to give you an idea of scale, let's zoom in the things. Let's zoom in whatever we see, whatever we know. We start with matter. Matter, you see a typical small cube of wood, 5 centimeters, let's say, more or less. So that's 10 to the minus 2 meters. And then we zoom in. I'm quite sure that most of you know that everything is built of atoms. So an atom is what we call 1 angstrom big. An angstrom is 10 to the minus 10 meters. So we zoomed in quite a lot. We scale. We go more than 1 million times smaller, something like 100 million times smaller. And then I think most of you know as well that an atom is built out of a nucleus and electrons around it. So the nucleus is quite a lot smaller than the atom itself. It is 1 picometer. So the P is for pico in this case. Now, a picometer is 10,000 times smaller than the atom. So when people say the big emptiness of an atom, this is exactly what they mean. You have the atom, and then you have this tiny, tiny thing inside, which is 10,000 times smaller, and in between it's a vacuum. There is nothing. We go even smaller. The nucleus is built from protons and neutrons, and this is a femtometer. Ha! I guess you thought that the last one would be femto. Well, no, this one is the femtometer, 10 to the minus 15 meters, quite small. It's the size of a proton. At the LHC, in all typical machines that we use in particle physics to accelerate, we typically accelerate protons. So the LHC is a proton machine. These accelerators are proton machines. So they use femtoscale to probe deeper into physics. We go deeper and deeper. We try to see inside the proton. A proton is built from quarks, which is even 1,000 times smaller, which is an atometer. Okay, this is just, scale, size of things, going from normal matter inside smaller and smaller up to femtometers and even smaller atometers. Now, the thing is, where it gets interesting for us, is how do we look at these things? What kind of machinery do we need to be able to see these small sizes? So, of course, for normal matter, we use our eyes, standard scale. Going up to atoms, let's say a bit bigger than atoms, we use microscopes. Going up to the size of atoms and inside the atoms, we use electron microscopes. So I'm a bit cheating here because an electron microscope is not really able to go inside the nucleus, but I didn't have anything bigger than an atom in my scale, so it's more or less the idea. But then, going even smaller, we need accelerator machines. Now, one of the first, let's say, famous accelerators was at CERN. This was the SC. This was the synchrocyclotron, sorry, which is this machine you can see here. So this machine. This was built in the 50s. And this is, you can see how big it is. This would be more or less the size of 1 human. So this is 5-6 meters big. Now, going even smaller, if we want to unravel a proton, see what it's built of, going into quarks, we need big machines. And of course, the most famous one is the LHC. The LHC, 27 kilometer, biggest machine we have. So we have some tendency here that we see the smaller we want to look, the bigger our machine needs to be. It's this kind of inversely proportional relation that is very typical for science in general. Okay, so resumingly big machines, they reach high energy by exciting protons, which are of femtometer size, and we use these to search for tiny particles. Okay, this was just the setting of the talk, a bit what we're talking about. Now we can really start. First things first, big machines. We need big machines. So these are particle colliders. We accelerate particles, we collide them. So what do particle colliders typically do? Well, they accelerate to increase the energy of the particles. They accelerate. This takes quite a lot of time to give them high energy. And at a certain moment, they start colliding. We smash two particles on each other to release an extreme energy. After collision, this will create new particles, which we want to detect. New particles or known particles. It will create lots of particles in all directions. This is what we are looking for. And then the last step, we analyze the results. We deeply probe the mysteries of life, the way we say it. We want to understand what everything is built of, how does everything work. Now, of course, this is not a particle collider. These are humans. Machines, they don't understand. Though this is changing, then we're talking about artificial intelligence, these kind of things. More and more in particle science, artificial intelligence is used as well. But at the moment, the collider does acceleration, collision, and detection. Now, the biggest example we have of a particle collider is, of course, the Large Hadron Collider. The Large Hadron Collider at CERN is like the pinnacle of modern physics research. It's the biggest machine in the world, 27 kilometer. Here at Geneva, I work at CERN, so I'm quite close to the machine. And it has been built, it has been conceptuated, let's say, in the end of the 80s. These things, they require quite a lot of time in preparation. Around 2000, around the millennium, people start building it. And at some point, let's say, things scale up. We start building for years. We need to dig a tunnel. We need to build the machine inside. And we need to build detectors around it, all these kind of things. It takes time. And then in 2008, we had a test run, which embarrassingly failed. And we lost one extra year. By the end of 2009, 2010, we were running. And we had the first results. So there you can see it's quite big. We have an accelerator here of 27 kilometer big, and we have smaller accelerators in front. I will come back to that a bit later. So 27 kilometer long. It is built of 9,600 magnets, and it creates around 1 to 2 billion collisions per second. That's also a very important thing. Billion collisions per second. We need data. We need lots of data, and I will come back to this a bit later. We need lots of data because we need high statistics to be able to really say with high security, with high confidence, we found a particle, or we discovered, we have seen something, etc., etc., etc. So 1 to 2 billion collisions per second, this was the design goal. This is also what we reached today, lots of data. Now, I said 9,600 magnets. Well, then the point is, magnets, there is an issue with magnets, because an accelerator, we typically say, is built of magnets. But the point with magnets is, can we really use magnets to accelerate? So some of you who maybe remember electromagnetism from high school, we have something which is called the Lorentz force. The Lorentz force is a force that the particle feels when it is moving in a magnetic field, a charged particle, very important. So if you have a charged particle, and we have a magnetic field that is like this. So we have, for example, a north and a south part. So we can see it here. Okay, it's the opposite. South part up, north part down. So we flipped it up. And we have the magnetic field here. The particle moves like this in between. Well, it gets a deviation, which is the force, the Lorentz force. Now, the deviation is perpendicular, which means, that's why we have this, this hand there. This is the right-hand rule. If you have the field in that direction, the current, this is the movement of the particle, if you want, in that direction, then the force is in that direction. So in the example we have here, the field goes from north to south, so it goes north to south. The movement goes in that direction, so the particle experiences a force in that direction. It will be bent. Now, bending, bending is not the same as accelerating, of course. So we could say that the effect of the magnet is in a wrong direction, because the moment the particle starts turning, well, the movement turns as well, you see. And what you get is that particles just start spiraling. So there is no way of a particle to go faster when it is in a magnetic field. So we cannot use magnetic field in this way to accelerate particles. It is like pushing on a swing from the side. As I showed here, you're nicely having fun on a swing, and as somebody pushes from the side, it's going to make you move, but not in the correct direction. It's not going to make you accelerate. So no magnets. What do we need is an electric field. An electric field is the force for an electric field is longitudinal, which means that if the electric field is in that direction, particle moves in that direction, the force will be in that direction as well. And the typical thing what we use for that are called cavities. Now, cavities are these big things. Okay, you can see one here. This is an image from the cavities at CERN. Now, the cool thing, what I think is very cool, is that they are empty. So we have this thing, which is some kind of copper, and so would be more or less this size. It's a tube, it's a hollow tube, and there's nothing inside. What we do with this tube, you see it has this peculiar form here. I don't know if you can see my mouse, actually. Can you see my mouse? Yes, you can see my mouse. Okay. We have this peculiar form here, which goes, if you have the cylinder coming in, it makes this bulge here. And it's exactly the form that makes the particles accelerate. Now, this is the main point. It's hollow, but the form is very important. What we do is we put an electric field on the exterior of this cavity, so on the copper itself, and it will create waves, standing waves inside. That's the classical explanation. Now, there is a more intuitive explanation. Now, you maybe remember from high school physics that electric charges in general, they either repel or attract, depending on whether or not they have the same charge, positive or negative. So if you have a positive particle here and a positive particle here, they will repel. If you have a positive particle here and a negative particle here, they will attract. So like charges repel, opposite charges, they attract. And that's exactly what we're going to use. So imagine here, this thing, that's a proton beam. So this is a proton coming in somewhere in the accelerator. And this thing is how the field looks in the cavity. So the field, of course, has two sides. It has a positive side and a negative side. So what will happen in the beginning is that it is opposite. We have this side blue. So blue means negative. And this side red. Red means positive. The proton itself is also positive. So positive here, the proton. Negative here. So remember, it has to start flipped. Blue and red. And they will attract. So the proton will be attracted towards this part of the magnetic field. And the moment it's here, it will flip. And this part becomes red as it is now. And this part becomes blue. And then we have red, red. So it repels. And actually, it pushes the proton away. So first it was attracted. The moment it's here, it is pushed away. So it goes even faster. And the moment it is here, the field flips again. What happens? And this becomes red again, and this blue, and it is even pushed further. So we have this like synchronization of the field, which is timed perfectly with the speed of the proton. So attracted and pushed. And so at every step this happens, the proton accelerates and goes faster and faster and faster. So every time it passes, it will gain some energy. Now, of course, for this, a correct timing is crucial. So this is what we call radio frequency cavities, RF, because the frequency at which they are changing is very high. This is in the order of 400 megahertz, something like that. I don't know it by heart. Now, megahertz means million changes per second. So we have something like 400 million times per second that it changes up and down from positive to negative. This is timed perfectly with the movement of the proton. Okay, so then, of course, the point is, I said the LHC exists of 9,600 magnets. So why does it have magnets? And why so much? Why so many magnets, 9,600, if the magnets actually cannot accelerate? Well, here comes the point. Scientists in general, we like to, okay, I'm not going to call it lie, because lying is like very, very negative, but we are lazy, and we don't want to, let's say, spend a lot of time explaining all the details, and so we go in like, So magnets. The truth is actually that the LHC has only a very, very short, very small part of it, which is the accelerator itself, something like 30 meters out of the 27 kilometers. So calling the whole machine an accelerator is actually a bit stretch, but it's just, we are too lazy to say every time, well, we have a 27 kilometer machine which has 30 meters of acceleration, so we call it an accelerator, because in the end, the whole goal, the main goal of the machine is acceleration. Why then is it so big? Well, let's see what these magnets do. We have different types of magnets. Now, the main magnet, the most famous magnet that most people know, is a dipole. A dipole is used for bending. What is a dipole? Well, a normal magnet that you know, the typical magnet north and south, that's a dipole because it has two poles, north, south, nothing else. So a dipole does exactly what we have seen before, the Lorentz force thingy. It will bend. So why does it bend? Well, because we have a machine with an accelerator of 30 meters, but we want to get these 30 meters and use it again. So we want to send the proton back here, and again, and again, and again. Why is it so big then, the 27 kilometers? Because at these extreme energies, these particles are of extreme high energy, the highest that we know in the world, at least. Well, it's almost impossible to bend them. You can imagine that the more you want to bend them, the more force you need in the magnetic field. And we are now at a technical limit. This is the technical limit. Our magnets can just, it's impossible to make them stronger at this moment. So this is why we have 27 kilometers, because this is the minimal radius we can have actually to keep the protons in track. And so every time we pass by, 30 meters of acceleration is gained. And then you might say, well, would it not be more interesting, or let's say more efficient, to not use a circle and to just make a very long line of only acceleration on electric fields? Well, this is possible and it exists. These are called linear accelerators. And well, there are examples of like SLAC is 2 times 2 kilometers for 2 beams colliding, so 2 kilometers. 2 kilometers is way more than 30 meters. However, we have 30 meters of acceleration, but our particles move fast. Several times per second they will pass. How many times? Well, 11,000 times per second they pass by. So after 1 second, we got the equivalent of 33 kilometers of acceleration. That's already something. And we don't accelerate only 1 second. The LHC, it has phases, let's say. We start by filling the thing with protons. This takes some time. When the whole ring is full with protons, then we start the acceleration. This takes 20 minutes. So 20 minutes times 33 kilometers per second, that's a huge accelerator, impossible to make in the linear case. So that's why we have a ring. And that's why we have a 27 kilometer ring, which is mainly built of bending magnets. What other magnets we have are quadrupoles. So look, this is one of the types that physics is really easy. 1, 2, 3, 4. Quadro. So 4 poles. Now, of course, this is not north, south, east, west. That would be too cool, but life is not always that cool. It's north, south, because magnetic fields have only 2 polarities, north or south. But we have 4 poles, north, south, north, south. The field lines, they go a bit like that. So it's like a curved star, which means that in the middle of the magnet, you don't see any field. On the sides, you start seeing the field. So what it does actually, it will push particles back to the middle. So it is as if it is focusing the beam, which is a very important thing. Without these focusing magnets, we lose the beam before it makes one turn. Now, there are several details. We cannot focus horizontal and vertical at the same time. There are all these issues. Maybe we can discuss this later if there is more time. And then we have higher orders. We have, like you see, sextupole, 1, 2, 3, 4, 5, 6, octupole, 8. In the LHC, we have decapoles, 10, and even dodecapoles, 12. Always in orders of 2, because you have combinations of north and south. What they do? Well, they do other stuff. They do corrections and things. Let's not go in these details. So we have the layout of the machine. So whenever people tell you the LHC is a big circle, well, that's another, let's call it a white lie, because we're too lazy. It is more like so also this, let's be honest, also the figure here is not exactly correct. Why is that? Well, it's more of an octagon of which the corners are bent. So why is that? Well, the moment you do something, let's say you put a detector, or you put an accelerator, the 30 meters acceleration, or you do other stuff, well, there you don't have bending magnets, right? Because you have a detector or an accelerator. Well, if you don't have bending magnets, it will not bend, right? These things are only logical. So you have typical accelerator has straight sections where we do the interesting stuff, and then bends, well, where we bend. And an LHC has typically 8 straight sections. So they are called octants here. We have the octant is combining part of the arc, but anyway, so these are the 8 straight sections. We call them the IPs or the IR, interaction regions. This is where the stuff happens. So you should imagine that one arc, one bend, so 1/8 of the ring is 2 to 3 kilometers, and then we have some 600 meters straight. So there are 4 things with a star here. You see, this is 4 places where the beams cross, 4 places where things really happen. So these are the detectors. These are the 4 experiments that the LHC have. That's why the two beams cross. So blue and red are the two opposing beams. Of course, if you want collisions, you want them, well, to collide. So you want to cross. That's why you have 4 crossing points. What do the 4 other points do? Well, one is a very important one because it's acceleration. So this is the place where the acceleration really happens.
Fred,
We have the beam dump. Well, at some point, as I told you, the thing goes in phases. We start filling it, we start accelerating, then we start colliding. This takes time. Well, we have quite a lot of protons inside, 10 to the 14 protons. Yeah, more or less it. I'll let you calculate how you would pronounce that number. So we had, this is the amount of protons we have. And of course, then we start colliding, as I told you, 1 to 2 billion collisions per second. So 1 to 2 billion collisions, every collision you lose 2 protons because you destroy them. So that's 4 protons, but then per experiment. So let's say these main two get most of the collisions. So we lose something like 10 billion protons per second, which means that you will see after a few hours that you have way less protons left. Of course, if you have less protons, you will have less collisions. So this is a coupled equation. So you'll see that the rate of collisions goes down slowly. You start at 2 billion and you end up at, well, this goes on for infinity because the less you have, the slower you will lose your protons. Okay, I will directly go to the last step of this, which is the beam cleaning. So we have the experiment, we have the acceleration, we have the dump. What does the dump do? Well, I forgot to give the main point. At some point you say the number of collisions is not high enough, dump and start over. You do that here. And then you need some cleaning in between. Okay. There are some questions.
Yes.
Probably.
Yes. Okay.
Barbara.
Frederik, so there are a lot of questions.
Sorry. Okay.
Yes. Can you hear me?
Yes.
Frederik? Yes. Oh, voilà. So there is first questions is if the particle collider, this particle collider is always working. I know the answer, but maybe you can answer.
Okay.
This particle collider is always working.
So I have a small issue, which is that I get your voice twice and my voice as well. So I mute
even mine
again. So if the particle collider is always working, well, pretty much. We on a whole year basis, we have 9 months of operation and 3 months of stop. In the stop, we do maintenance, we switch some small components and stuff. So typical maintenance, and we save energy. The 9 months of operation, this is pretty much non-stop. So as I told you, it's phases. We start filling, we accelerate, we collide, we dump. We need some setup time before we can start again. But then this happens day and night, non-stop, yes.
Okay, thanks. And then we have a less easy question. Question is if you need to change the charge of, I don't know, was the magnet 1 or 2 billion times per second in each radio frequency cavity. So probably some details about the radio frequency. Times per second in each radio frequency cavity.
Okay, can you maybe at in the same time also type the question? So if I understood it correctly, whether or not you have to change the charge of the field so many times per second, is that correct?
Yeah.
If I understood correctly, whether or not you have to change the charge of the field. Sorry, this is really. So this is true. This is exactly what you need to do. Sorry, I'm going to put it a bit softer. So the magnetic field, it has, let's say, a polarization. It has a positive side and a negative side. It's like a wave. It's like a wave. It has the top of the wave. Actually, we can show that if we go back. Okay, so you see it has a positive side here and a negative side here. So by the way it's moving, you say you change the positive and negative sides. If you stay in this spot here, which would be the place of the cavity, and the wave moves by, then you will see actually that it goes up and down. So it goes from positive to negative. By moving the wave fast enough, you get exactly this kind of sign change. So you don't need to change in charge 2 billion times per second. No, you need to change let's say the change is not related to the number of collisions. The change is related to the speed of the particles. So this is the speed of light, and this is how fast will they pass. It's the size of the cavity. When the moment they enter and the moment they leave, it needs to have changed. So the cavity is more or less this size. So you can measure yourself, I don't know, what is that, 20 centimeter, 30 centimeter, at the speed of light, and you will see, to be able to change in that time frame, you get something like 400 million times per second.
Okay, thanks. The very last question is, I wrote down, if you would be able to collide even mesons if you want, or if you have to have a different type of accelerator.
Well, in the LHC, we do not collide mesons. I don't think we could easily do that not because we cannot accelerate them, not because it doesn't fit, because this would all work, but because of beam stability and this kind of issues. It's more tuned for that, because you need to do a lot of things to, well, not lose your beam. This thing is quite unstable because you have so many protons that you cram together. I'm not sure if it would be that easy if you do it with pions, but of course, meson accelerators, they do exist. And basically out of a meson accelerator is exactly the same. You have accelerating part and you have magnets to bend, you have magnets to focus. The whole concept is the same.
Okay, thanks. And you can go on, because the other questions probably will be answered in the coming slides. Thank you.
Okay.
Thanks. And you can go on, because the other questions probably will be answered in the coming slides.
Okay, we were at the accelerator, so this was how the LHC looks like. So, as I said, it's quite complex. We don't just have the LHC, we need to build things up. So we cannot just put the protons inside the LHC directly. Why? Well, because simply, if the protons are almost not moving in the beginning, then the magnets would be very, very weak to keep them in such a big machine, right, to 27 kilometers. And on magnets, they would have to change from very weak to very strong in extremely short amount of time. They're not able to do that. If you change them so fast, they will break. So we build up in stages, and we start here, typically. If you can see it, it's called LINAC 2. That's a linear accelerator. So that's also some 30 meters of linear accelerating to get them some basic acceleration. At the end of that, they're already at 30% of the speed of light. Then to go to a small 157 meters, the booster. Then they go to a bigger one, the PS 628. Then to an even bigger one here, SPS 7 kilometers. And then they go in the LHC in two parts. You see one part here and one part here. Why? Because, well, in the LHC, we need two different opposing beams so that we can collide them. Now, all these steps, of course, they take time. And of course, you can see that in the booster, 157 meters, we cannot put as many protons inside as in a machine of 27 kilometers, because as I told you, it is full from beginning to end of protons. Not 100% full, it's packaged in these kind of things, but that's details. Of course, we cannot put the amount of protons that go in 27 kilometers in a 157 ring. So this goes in, let's say, in phases. We fill the booster, and then it goes to the PS. It's not full, it has to do it 4 times. Well, the booster has actually 4 rings on top of each other to do that in one go. So whenever we fill the booster, we fill the PS. And then the PS goes to SPS, 7 kilometers. So this happens booster PS a few times, booster PS, booster PS, booster PS, until the SPS is full. Then the SPS accelerates, and it fills the LHC. This is, of course, again, only a part of the LHC. This happens, all this thing, a few times until the LHC is full. And then we can start acceleration. So these are the steps. So all the other things you see here, all these other small things, these are side projects of CERN. We have all this machinery, and it would be a shame not to use it, because the moment the accelerator is full, this is only a matter of a few minutes, and the LHC is full. And then it will start accelerating, it will start colliding. This takes hours. All these hours, we are not using all the other steps, booster, PS, SPS. That's a shame, that's a waste of resources. So while the LHC is doing its thing, the other ones, the steps before, we call this the injection chain, can be used for other experiments. And so that's why I have all the side experiments here. Then a small thing about detectors. So we have 4 detectors, we have 4 experiments. We have CMS Atlas. These are 2 big ones. NHCB and ALICE. This, for example, is CMS. It's a schematic of CMS. what I just wanted to tell you is that detectors, they have to go in different layers. It's a bit like an onion, so different layers on top of each other, to be able to actually see different particles and to distinguish whatever we see. We have typically 3 types of layers, so I have a side view. There exist way more than these 3, but this is what we use in the LHC. We have here, the first thing, these are called trackers. The second thing here are calorimeters. This is the green part and the yellow part. And then here we have muon chambers. So 1, 2, 3. What do they do? Well, what they do, trackers, they track. They show literally tracks of particles that pass by. This only works for charged particles. Calorimeters, calorie is some old unit for heat, actually. A calorimeter does what it sounds like. It destroys a particle to be able to measure its energy. So it heats it up between brackets. That's not true, but old machines, they still exist, actually. The real name of a calorimeter is actually a machine in which you put food, you burn it, and you see how much heat you get, because then you know the energy containment of food. So if you have your Snickers bar, you see, whoa, 560 kilocalories, that's quite a lot of, and you'll get fat if you eat too much Snickers. How do people know this is 500 blah blah kilocalories? Well, because they put it in a calorimeter and burn it. So it's a bit the same idea here. We put the particle inside, we burn it, we don't really burn it, we absorb it. So the particle, this will be a very dense material, and the particle will be slowed down inside the material and stop. It lost all its energy. But you probably know energy cannot be destroyed. Energy can only be transformed. So the energy is not lost. The energy goes to, for example, heating up the material or radiating light and all these kind of things. So if we measure this, if we measure the temperature or we measure the emitted light, then we know how much energy this particle had. So the calorimeters destroy the particle to get an idea of the energy. And so these are the first 2 steps here. So you can see some tracks. For example, this red line here, it's an electron. So we have a big magnet here, the superconducting solenoid. It's like a cylinder, and it bends the particles that are generated. The reason it does it in the detector, we're not talking about the accelerator, is to aid detection, because then we know if it bends left or right, it will depend on the charge. So bending left, in this case, if you look like that, negative, positive in that way, then it's positive if it bends in the right way. So the bending helps us to, let's say the bending is only used for analysis. So we see a particle bending here, particle bending other way, so this one is positive. So we see we have 2 different calorimeters. Why is that? Well, light particles will be stopped in this one, heavy particles will be stopped in that one. So we see a light negative particle, electron, a heavy positive particle, for example, proton. And then we have these dashed lines. I don't know if you can see that it's dashed, but dashed means no track. So we cannot really see the track. We cannot see it at all because it's neutral. And if it's neutral, it also doesn't bend. So we just get a signal suddenly here. Well, we don't care that we don't see the track because we know it is hence neutral and not bent. So we can just draw a line. And we see a signal here. So what is this? Well, it's a neutral particle that is light. Photon. Neutral particle that is heavy. Neutron. So, of course, this is very simplistic. This, let's say, it doesn't help you to distinguish between a proton and other types of heavy positive particles. But we have analysis to that, and we don't always need to do so. Sometimes we want, sometimes we don't. Then there is one particle that, for several reasons, actually can still go out. That's this blue line. That's a muon. A muon is not super heavy, but the way it is created, it has a lot of energy, and it's able to penetrate completely. And so what we have after the magnet, these are the muon chambers. Why? Because, well, whenever something comes there, we know it's a muon. So these are just the muon detectors. So we can see here in the onion, we have trackers inside, the yellow and the blue thing, and then the green is the light calorimeter, yellow is the heavy calorimeter, this is the magnet, and here the muon chambers. It's quite big, huh? As you can see, this is a human, so we get something like 15 meters diameter, I think 30 meters length. It's written here, yeah, 30 meters overall length. So that's a big machine. Okay, so we had step 1, big machines. Example of the LHC, accelerators, detectors, all those kind of things. Now we go to step 2. We're talking about tiny particles. This is my my trial, let's say, my attempt to make you understand why are we doing this. I mean, what is the whole point? Why investing so much money? To give you an idea of scale, the LHC costs something around 4 billion euros to construct, and another few billions for the detectors, and then all the infrastructure. You need to pay all the people. So it's expensive. Now, on the whole European budget, it's nothing. People always say it's like 1 coffee per year per inhabitant of the European Union. Not Union, but the member states of CERN. It's not exactly the same, but more or less. But still, a lot of money. Why? Well, since the beginning of time, since people had, let's say, a conscious mind, people have been asking questions. Questions like, what are we made of? What is the universe made of? Is it the same as we? And how does it actually work? How does the universe work? How do these things work? And we have all these kind of questions. It starts in philosophy, ends in science. Sometimes it's the opposite. Well, for that, actually, I have this amazing plot, which I believe to be the most beautiful plot in the world. I call it the basic bricks of the universe. What does it show, this plot? Well, on the horizontal axis, you see BC AC, before Christ, after Christ. So this is the year, actually. So this is a scale of years. On the vertical axis, it's different kinds of basic matter. In other words, how many elementary basic bricks do we believe everything is built from? Now, it starts in the beginning of times, ancient times. People had no clue. And water is water, stone is stone, earth is earth, wood is wood, everything is just. But then you had the Greek philosophers, the nature philosophers. And the first one, not the first one, but the first one with a very, let's say, well-defined view on this was Empedocles. Empedocles, he said, everything we see around us, every material, all the matter, is actually built from 4 basic elements: water, air, fire, and earth. That's actually quite a cool idea, because you have to imagine that, let's say, from a conceptual point of view, for us it's very normal, because we have been raised in the idea that everything is built from atoms. We have been raised in the idea that everything is built from small things, and then the way you structure, the way you organize everything, you get wood or you get water. It's like Lego from a very far away side. For us it's easy, but if nobody ever told you that, it is a very, let's say, it's a very difficult, a very high conscious step to say, whoa, but you know, actually everything is the same. It's built from something deeper. That's a very deep philosophical thing to say. I have quite a lot of admirement for these people. There was Empedocles with the 4 elements. There was actually Democritus, which was the first one to say, well, what is more important? Everything is built from small things. He did not specify it. He did not say it was earth, water, fire. He didn't specify, but he said what is very important, these small things are indivisible. You cannot divide them. Not indivisible, indivisible, divisible. You know what I mean? You cannot split them in smaller pieces. These are the elementary bricks. And he called them atomos, undividable. You cannot break them up, atomos. So we honored him by calling these things atoms. He was the first one to conceptualize this. I'm very much impressed by that. And then you see we go, let's say, as the time grows, our concept, the common view of people was, well, we have more elementary things because, so this is Empedocles, look at him. Yeah, very nice guy. Then a bit later we get the medieval ages. Look, these are alchemy symbols. So people are saying, yeah, we have basic elements. We have a lot of them. We have gold, we have bismuth, we have silver, and this kind of things. And then they were like, we have lead. Maybe we can move from one element to the other, change lead in gold, blah, blah, blah. The basic idea was cool. And then this rises over time, and then suddenly you have this guy, Mendeleev. Look, that's Mendeleev. And he says, well, we have quite a lot of elements, and we can organize them in behaving similarly or not. This is his famous table, of course. And then this is like somewhere just, I think this is a bit off. I think this should be 1895, the jump down, but never mind. So somewhere here we have some 80 elements, a bit more. Not all elements were discovered yet. And then you have these cool guys. This one is Rutherford, who is actually able to show, all these different elements are actually a nucleus with electrons around it. Bam! From almost 100 particles, we go to 2. I love this. Puff, we go down. Everything is built from 2 particles, people. Protons and neutrons. Sorry, no neutrons. Protons, electrons. Neutrons were not yet discovered. So this is Rutherford and Niels Bohr, who made the first model of the atom, and blah, blah, blah. So at that moment, suddenly this was a huge world shift. All these things, no, the whole world is built from only 2 particles, protons and electrons. Cool, right? And then this grows because then they discover, there are also neutrons. There is also muon. There are also neutrinos. Tac. And then people start discovering, but you have these kaons, pions. So somebody called it in a question, mesons. These are, for example, pions and kaons. But then we have delta particles. And all this, people were discovering more and more particles. And in my impression, this actually should go higher than before. And then there was this guy, Gelman, who started organizing these kind of things. It's the eightfold way, which actually comes from Buddhism. This is the 8 ways to live and blah, blah, blah. But then he used this name to organize, all these particles that were found in a structure. And then because of this structure, people started realizing, oh, so if, again, like with the table of Mendeleev, we can organize them based on properties, probably this means that there's something, deeper, showing what they're built from. And then people are like, oh yeah, they're built from quarks. And poof, we fall down again. Now we have, at that moment, I don't remember, we have probably 3 quarks only that were found, 3 quarks, electron, photon, and so the number of particles was quite small here, but more than 2. And this is where we're now, and we've started discovering new and more particles, so a few more quarks. And the last step here, this one, of course, is, so this is the standard model here before, forgot to mention it. So then people started organizing all particles that were known into 16 particles. We have 6 quarks, 6 leptons. Electron is a lepton, so we have lepton-like particles, and then force particles here. These are the 3 people that are the founders of what we call today the standard model, Glashow, Weinberg, and Salam. And then the last jump here, this last jump, is of course the elusive Higgs particle, which was found 2012. So this is Brout, Englert, and Higgs, the 3 that made the Brout-Englert-Higgs theory that explains why particles got mass. So this is where we are today. We are at 17 particles. We have 17 elementary particles. This is why I like this plot so much, because it has this oscillation. We go down. So maybe one day we will fall down again and see everything is built from, 2 particles again. We don't know that yet. It's the evolution of the basic understanding of the universe. So this is the standard model, as we know it today, 17 particles. As I said, 6 quarks, 6 leptons, 4 what we call gauge bosons, which are the force carriers, and then the Higgs boson. Everything we know is built from this. Everything we understand is encapsulated here except gravity. So to understand that, we have to go to the next step. And I think maybe this is another good moment to break. Are there questions?
Yes, a lot of questions. So the first one I'm going to copy for you is back to the accelerator complex, how you can see the trajectory in the accelerator without affecting their path. So it may be a quite technical question, but I think that is really taking the point.
Okay, that's actually a very good question. Well, you do not affect. So you affect their path, actually. This is a very good observation. You do affect their path, but very slightly. I mean, I don't think it's even measurable. The point is that particles have such a high energy when they're created, high energy. And so by detecting, you make some interaction which might deviate them slightly, but since the movement or the energy in that direction is so high, this is so tiny. Very, very slow particles will be slightly influenced, but we have something which is called delta rays, delta particles, delta rays, which is a particle that actually goes through a gas. We have gas detectors. It will make small side sparks along the trajectory, which is where it actually moves a bit because it emits small radiation particles. But we can ignore it. That's the main issue, the main message, sorry.
And another question really interesting is why an electron is absorbed by the electromagnetic calorimeter and a muon doesn't. So we have to enter in some radiation matter interaction. Is again a bit technical, but can be interesting.
Okay, there are some. Okay, the easy way to explain is because a muon is 200 times as heavy as an electron, so it has more inertia, if you want, and it goes through. Now, that's a very lazy explanation because it doesn't explain why a proton, which is almost 10 times more heavy than a muon, then is absorbed. So there is more to it. There is, let's say, it's because it's a lepton and it's heavy. That is the main short answer. There are only a few leptons, so we have the electron, and the muon is a heavy electron, and we have one heavier, which is a tau. So the tau would be able to go through as well. However, the tau is unstable, and it decays in I don't know, femtometers? No, not femtometers, but probably something like picometers. So very fast. You cannot. It does not have the time to go out. But so the reason is that leptons, they are, let's say, the number of interactions they can do, the things they can do, are limited compared to a proton. So it has less interaction going on while going through. I hope that more or less answers the question.
Yeah. And a very last question. In your summary table, antimatter is not taken into account. So someone already anticipate maybe some other topic, but in the number of elementary bricks, you didn't. We are not counting the antimatter particles, antiparticles.
So very good question. The reason is that, well, matter-antimatter is more considered as some kind of symmetry operation. So there is the what we call charge conjugation operation, which changes a particle into an antiparticle. So from a fundamental point of view, a particle, its antiparticle are the same particle in different states. So you could say like the electron state is an electron or a positron, depending on it's like particles have spins. Electrons have spin. They can be spin up, spin down. You would not call a spin up electron a different particle from a spin down electron. So there is no reason why you would call an electron a different particle from an anti-electron. Why do we do that? Well, historically, because in the way they were discovered and stuff. So you could add to the standard model all the antiparticles. I prefer not to, because for me, they're just different versions of the same particle. If you do that, you should do the same for color, because, you know, quarks and the strong force, they have a property which is called color. We have red quarks, we have green quarks, we have blue quarks. So then you should have 18 quarks and 18 antiquarks. So some people count like that. Then you end up with 18 quarks plus 18 antiquarks, 36 plus 6 leptons, 42 plus 6 antileptons, 48 plus 4, something 60. But for me, they're all the same particle, different states, so 17. I like it simple.
Okay, I think that you can go on. There is a recurring question about the spin of the particle, but maybe we can comment on later. Can you explain what the spin of a particle is, and how can they have half of this kind of fraction? So I think that is very basic question from quantum mechanics. I don't know if you want to comment.
Okay, so spin. Well, why is it 1/2? Well, the reason is, of course, the spin is not 1/2. It is 1/2 something, because we're talking units here, right? When I say this block of lead is 1 kilo, well, it's 1 kilo. If I would express it in pounds, it's a different number. So you choose a unit. So for spin, it's 1/2 something. So that's the unit. Why did we choose 1/2? Well, because people started noticing that the allowed spins for a particle depend on properties of the particle. So standard particles, as we know them, protons, electrons, they have 2 allowed spins. Spin up, spin down, plus 1/2, minus 1/2. Now, you want this to be symmetric around 0, let's say, right? So plus 1/2, minus 1/2. Then there are other particles, like bosons, which have 3 spin states. And then they are, because you want it symmetric around 0, plus 1, 0, minus 1. So they have whole number spin, while the others have half number spin. Then 4 spin states would be half again, 3.5, plus 3.5, plus 1/2, minus 1/2, minus 3.5. 5 spin states would be whole again, plus 2, plus 1, 0, minus 1, minus 2, etc., etc. So this is why the 1/2, because it fits more in the way we organize stuff. But again, it's a choice, because it's a choice of units. But in that unit, for all particles, not only protons and electrons, but for the whole bunch of possible particles, things work out a bit more nicely. Choices.
Okay, I think that you can go on with your slides, and let's go to the end of the lecture.
All right. So, high energy. So now comes, we had the big machines, which is how we do it. We have the tiny particles, which is what is it about? Why do we, what are we trying to understand? And then we have the high energy part is more like, well, what is the theory behind it? How is this driven? How does this standard model now work? I have this very nice comic from XKCD. Oh, I forgot to put the credit. So this is XKCD. This is a nerd comic. It's very nice. It actually captures the basic idea. We have what we call the basic forces of universe. So the 4 fundamental forces. We have 4 of them. And this is actually that describes how particles will behave. Well, the one that is most famous is, of course, gravity. Because you have things, you drop them, falls down. So this was the first force to be understood, to be described. It was Newton and blah, blah. And then a bit later, people realized there is also something like electromagnetism. Electromagnetism, it was discovered with the inclusion of electromagnetic rays. This is like Maxwell. So this is the 19th century somewhere. And this was developed. And then when they started working in the 20th century with particle accelerators and stuff, when they were discovering actually all these bunch of particles, the mesons, the pions, the deltas, and all these things, and then a bit later the quarks and binding together, they discovered there's even another force, the strong force. So let's stop here. What did we have? We have gravity. What does gravity do? It attracts particles by mass. The sun pulls at the earth pulls back a bit, very tiny because we don't have much mass. You drop an apple, earth pulls on the apple. Apple pulls the earth up a bit, again, very, very tiny amount. Gravity. It's typically this inverse square law. Electromagnetism, it's a bit a similar thing. Positive particle or positive charge, negative charge, attract. So we have this again, this what we call inverse square law, attract. Things get a bit more complicated with that because then you have the inclusion of actually wave theory. We have field theory and how these waves think. And so you have Maxwell equations. That's quite complicated. The basic statics, what we call electrostatics, is very easy. This is the same way as gravity, but now with 2 possible charges, plus and minus. Gravity only attracts. Electric charge, electromagnetism, let's say electric charges, they can attract or repel. But then this thing gets a bit fishy. Huh? This is the beginning of bachelor physics. It's nice, very cool, however, not so easy. And then, well, people realized there is something finicky, there is something strange with these atoms, because you have all these protons together, right, in a nucleus. You have this very small, tiny nucleus with lots of protons inside. Well, how do they stay there? For example, carbon, C12, has 6 protons, 6 neutrons. But all these protons, 6 protons, they have positive charge. They should repel. Why do they stay together? Well, because there is another force, and it's strong, because it overrules the electromagnetic force. So that's why they call it strong. Easy names, right? It's stronger than the electromagnetic force, and it holds them together. However, it has this particular property that it's very, very tiny localized. You go outside of the nucleus, and already the electromagnetic force dominates again. So it's very short range, so to say. You don't have an easy formula like this one to describe how that works. Then it goes more complicated, and you need field theory, quantum field theory. So that's why here, well, he says, well, hold protons and neutrons together, because there is no easy formula anymore to show it here. And then the last one, the weak force, well, it's even more complicated between brackets, because this is fully into quantum field theory. It was discovered even a bit later than the strong force. So the strong force, keeps the protons together in the nucleus and also keeps the quarks together in the proton. So that has 2 regimes. We have the strong nuclear force, keeps the protons together in the nucleus, and then the strong force typically keeps the quarks together in the proton. So you could say in a way that the LHC, or any particle accelerator that uses protons or mesons or whatever, hadrons, is a strong force machine. Because what it will do, it will smash open the protons, you get the quarks, and then they interact with it. So the first thing that happens is strong force. And then whatever new physics you will find will be inside strong force machines. Cool thing, strong force. The last step, the last thing that was discovered was the weak force. The weak force, what does it do? Well, it is radioactivity. It changes particles. All these things up to here, They don't change particles. They attract or repel. Does things in an easy way, a bit less easy way, or not so easy at all way, but it's always the same. It's about keeping them together, repelling them, about dynamics. The weak force changes them. What it does, for example, it can change a neutron into a proton. You know maybe that a neutron is it decays. You keep a neutron for free, let's say, whoops, and in 9 minutes it will decay to a proton and send out other stuff with it. And the weak force also make muons decay and all these things. So what we call radioactivity, alpha, beta, gamma stuff, is the weak force. Now the weak force, well, it's fully in quantum field theory, and to describe it again, you don't have an easy formula. It gets a bit more difficult than the strong force even. So that's why the mumble, relativity decay, mumble. Let's say that from something which is very easy to explain and have a very easy mathematical law, it goes more and more difficult into, at some point, well, you can just say what it does, but to give people an easy feeling of how it works, it's totally forget it. And now, of course, the bottom line of this thing, the cool thing, of these four, there is one which, well, we don't understand at all how it works on a small quantum level. And then you would expect maybe that's this one. Well, that's actually gravity. So the one which is the easiest to explain, the easiest to get the formula, it seems virtually impossible to actually see how does it work on a microscopic level. How does the quantum level work? It destroys itself if you try. If you try to understand how is the gravitational force, how is this force transmitted, it just doesn't work. That's cool. That's why theory, let's say theoretical particle physics and these kind of things get so interesting and cool. So 4 forces, that's the main takeaway: gravity, electromagnetism, strong force, weak force. This one changes stuff. These 3, without gravity, are fully described in the standard model. The standard model, which we had here, twink, all these things. And that's why we have these 4, we call them the force carriers. These are particles that transmit the force that we're talking about. So the photon transmits the electromagnetic force. So if you see 2 magnets, or if you have 2 magnets, you don't have to see them, and you know what happens with 2 magnets, north to south, smash. If you have very strong magnets, don't put your finger inside, it can hurt. Just read an article about a scientist putting it in his nose, not smart. Don't do this kind of things. So up, we typically are taught that this is the magnetic field stretching out and the fields and chuck. Well, we understand now that what is actually, in reality, what is happening, there are no such thing as fields. What is happening, it's just photons. Photons sending out all the time. And every time a photon enters one magnet, it's like kicked closer. And this happens billions of times per second, billions of photons and stuff. So it's not a field, it's just photons everywhere. Photons carry this force and make them attract. Now, for the strong force, we have something similar with gluons. We call them gluon. Why? Because they glue the protons together in the nucleus. And we like cool names, and you know that. So the gluons, they glue the quarks together in the proton and keep the protons together in the nucleus. Okay, this is actually not the gluons, but blah, 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 blah. The gluons glue quarks together inside the proton. And then the last one, which we understood, was the weak force. There was W and the Z boson. We have actually 2 W bosons, so we have 3 of them. W plus, W minus, and a Z. So 3 weak bosons, and they will actually do this. So whenever we say the neutron changes into a proton, this is because there was some W involved that changed it. Then the Higgs boson is a bit particular because it's not really a force. It works in a bit different way. So I'm very sorry for all these notifications. I have no clue how to put it off. Okay, so 4 forces: gravity, electromagnetism, strong, weak. And these 3 are inside the standard model. This one, no clue. We have a very, very good theory that describes gravity. It is Einstein. It's Einstein, the general relativity. But this describes it at the macroscopic level. It describes how stars are formed, how galaxies behave, and how even light is actually bent by gravity, black holes, all these things. But that doesn't explain how it works, what is really happening at the microscopic level. Open questions. So, how do we actually do it? Whenever somebody tells you, we found the Higgs, probably most of you will know that 2012, we found the Higgs LHC. We are very proud. I work here. I'm so proud. The Higgs boson, finally found. People wanted to find it since the 60s. That's a very long time. Fruitlessly, effortlessly, they have been looking and not finding it. And now they found it. Huh. So that's again one of these white lies, in the sense that nobody has ever seen a Higgs. And I don't mean humans. I mean also our detectors. We don't see the Higgs. Why? Well, because it's unstable and it decays before we could be able to see it. It decays so fast that you cannot see it at all. So how do we know that we have found it? How do we know we have created it? And that's where the black box mechanism comes in. It's what is happening at the collision of the particles. We don't know. We have no clue. We know what we put in, 2 protons, push, poof. We measure what comes out, all the particles, and then we use statistics and the theory we know to deduce what actually happened. That's how it looks. You see, we have a nice black box in the middle. That's where all the shit happens, as they say. Proton-proton collision, stuff goes out. So what does that mean? Well, the new physics, of course, is here. That's the main point. What does it mean? Well, statistics. This plot was a very famous plot in 2012 because this is the Atlas data proving that they have found the Higgs. So what does it mean? Let me try to explain. We have here, we are looking at a very specific set of events. What we call an event is what kind of particles go out. So again, we know what we put in, protons. We look what we get out. These things only shows all these collisions where we got 2 photons out. We get a bunch of other mess here, but we care about the 2 photons. So what happens? We have a proton here, proton here. Smash, protons break and go into fragments in all the... So, okay, whoa, very important distinction here. They break and go into fragments. They don't really. It's not that we break open the proton, see what is inside. What really happens, it's important, you know that, the protons annihilate, poof, gone, completely become energy, you know, E equals mc squared and this kind of result, shoop. And then this energy randomly creates new particles. So you can create from 1 proton, that has very high energy, you could create thousands of protons. So I think you agree that thousands of protons cannot be inside 1 proton. You have a definition with a problem with your definition in that way. So that's not what is happening. You just destroy the proton, you have energy, and you make new things. This could be more protons. So, bam, but for ease of communication, I say we break them open, we destroy them, break them open, fragments of the proton, blah, blah. Just realize these are not really fragments. You don't really break them open. So we break them open, fragments here, and we get all this chisel along the beam pipe. So this is the beam pipe, the protons come in. These things, we don't care about them. I mean, we do for some kind of things, but not if you are looking for the Higgs. But then what could happen is in between, in that direction, so perpendicular to it, something cool is created, namely a Higgs. And then what could happen is that this Higgs, for example, decays to 2 photons. So that would be a very clear signal. We would see lots of chisel here and 2 photons in that direction. Now, the problem with it is not only a Higgs does this. We have lots of other things that give the same. Remember, it's a black box. We don't see the Higgs. We have other particles like a Z0 boson that could create 2 photons. We have other particles like pi0 could create 2 photons. So, okay, pi0 you can see, but Z0 you cannot see. We're looking for particles that live short. And then we have just standard things. You could have photons radiating standardly without even creating a new particle in between. So you will not know the difference. However, everything except the Higgs has been tested thoroughly already since 60 years. So we know exactly how many times we should see these 2 photons on the number of collisions. So I'm now inventing numbers. Let's say per 1 billion collisions, you would see 50 times 2 photons. I think it is actually much lower than that, but I'm inventing. Okay, so this is all the things we know without the Higgs. Then we should see on 1 billion collisions, we should see at least 50 times, or on average, sorry, 50 times 2 photons. If a Higgs exists, it will happen more, because then the possibility of a Higgs creating is added to that, and you have more times 2 photons. How many times more? Well, not so much, because the Higgs is what we say elusive. It's not easily created, and you don't easily see it. So it would happen, I'm again inventing a number, let's say 0.1 times more. So instead of 50, the average would be 50.1. Well, that's a small difference. So if I do 10 billion collisions, no, let's say 1 billion collisions, 1 second, and I see 51 photons, did I prove that I have a Higgs? Well, no. because these are all random processes. If you throw a die, what is the average of a die? Well, the average of a die is 3.5. I'm quite sure if you throw once, you're not going to throw 3.5. But also when you throw 10 times, you might end up with an average of 5 because you throw quite high, or an average of 2 because you throw 10 times quite low. But if you throw it 1,000 times, 1,000 dice rolls, the average will be quite close to 3.5. So you need high statistics, we need a lot of data. So if I have 1 billion collisions and I see 51 times 2 photons, I have 0 information. It tells me nothing, pure random. If I have 1,000 billion collisions and I have 5,010 times 2 photons, that's already a bit more strong statement. So that's why we need so many collisions, to be really able to see that we added something. And so this is the typical plot that shows it. What it shows is we're measuring the energy of the 2 photons. Remember, calorimeters, we can measure the energy. So we measure the energy, and then this red line included with a dashed line, so not the bump here, but the dashed, that is actually what our theory tells us will happen. That's all the things we know. That is how many, so this vertical axis is counting events, so how many times does it happen for this energy. So how many times do we see 2 photons at an energy of 120 gigaelectron volts? So forget the scale, doesn't really matter, the unit. So we will see that happen 2,200 times, and then, okay, this is normalized per whatever, and also per size and blah, blah, blah. But so that's how many times we would see it happen. So we know how many times we have to see them. If Higgs exists, then this will happen more, but only at one very specific spot, the mass of the Higgs. So only here, this is the mass of the Higgs, 125, more or less, so 126.5, blah, blah. You will see it happen more. You see this bump. Because then, you know, a Higgs is created, and it creates more 2 photons whenever it's created, so at its mass. So now the point is, of course, how accurate is that? Because I can show you a bump, and it could be, it doesn't look accurate. You see all these bumps here. Well, that's why we need statistics, because you cannot trust human eyes. Right? There are other things you cannot trust on humans, but forget that. The human eye on this is like 0 information, because you would call this one also a clear bump, and this one. That's where you do your statistical analysis. And it will tell you that this is random, while this is not. And that's a very important observation. And that's why we use the statistics so heavily. And it will tell us, well, this actually is what we say significant. And then we can calculate what we call the accuracy. We can see how sure are you that this is. And it will actually show you bands on the plot. So we have this plot going down, the curve, and it will show you bands around it, like up a band. Now, of course, if this is the bump, and the band is bigger than the bump, well, then your bump is meaningless. You need accuracy. So by getting more and more collisions, the bands will narrow down, narrow down, narrow down. And if the accuracy bands follow the bump nicely, then you found something. And how these bands, how big they are, so how accurate our statement is expressed in what we say sigma, these deviations. So this, maybe somebody knows a Gaussian distribution, it tells you where in the Gaussian are you. So 1 sigma, this means you have something like 20-30% chance that it is just a random effect. 2 sigma, well, a few percent chance that it is just a random effect. 3 sigma, well, already very small. It's less than 1% of chance that it is actually purely random. So 3 sigma is what we say, I forgot the word, something like we found something, we found the particle, but it's not a discovery. It is an event, something has been discovered. And then you go for 5 sigma. 5 sigma. 5 sigma means that the probability that this thing here is actually just a random event. I mean, the fact that we have seen so many times more 2 photons, the fact that we've seen that at that energy, the fact that this actually is not really a Higgs, but just randomly it happened to be too much, this chance is less than 1 out of 140 million, something like that. That's a very small chance. The chance of you being hit by an asteroid is actually higher. So that's what 5 sigma means. So before something can be called discovery, you need 5 sigma. Higgs found, whenever 2012, people were like, whoa, Higgs is found, 5 sigma. So this is an example process that gives you, from a proton, we get a gluon, another gluon, and some other chisel here, creates a Higgs. And then after a while, the Higgs decays, but up to 2 photons. This thing is the black box. We see what we're getting, the 2 protons, we get out 2 photons. Inside, we don't know. This inside, what it really means, well, we have ways, let's say, we have theories, we have ways to describe what is happening in between. So this is quantum field theory. We have Feynman diagrams and all that things. I will skip over it a bit. This one is just to prove that you found the particle. Well, it still has to be the particle you are looking for. For the Higgs, it means it has to give mass. And this plot means that it does. If it would not, it would look like this, bloop. So the fact that it follows these lines, it was the Higgs, well, small plot. So these are the Feynman diagrams. We can discuss maybe later. So I had a small part about the future, but I think this maybe will get stuck, or I can maybe do it in 2 minutes. But first, let's see if we have a few questions.
Okay. Yes, Fred. There are a couple of there are many questions, and you will have to answer after the talk. But first, the question is if one single proton have enough energy to create many other protons. So I think that this is interesting to explain how this magic can happen.
Okay. Yeah, I should have known that this is a tricky one. So when we talk about energy, energy has actually several aspects to it. You have the energy due to movement, kinetic energy, and you have the energy due what you would call the inherent energy due to mass. If you want, in the old classical way of seeing things, this is potential energy. So the mass part is the typically known E equals mc squared, blah, blah. So that's the, to get from mass to energy, you multiply it with the speed of light squared. So that's the mass part. So the energy has this mass part, and it also has a movement part. Now, this is not just a sum, it's a quadratic sum, so you square and then sum, blah, blah, blah. Just know you cannot simply sum it. But these are the 2 components of energy. Now, what you do when you analyze the proton, you release the mass energy, and you get, it's like putting it in a mixer, you have all the energy available. So every particle that exists is a combination of kinetic energy and mass energy. A photon has 0 mass, so no mass energy. A proton that is not moving has 0 movement, so only, this is not my middle finger, only mass energy. Most particles in movement in a collider have both. Now, to give you an idea about scale, if you are running outside, you have your mass, your potential mass energy, and your movement energy, you will feel that your movement energy is quite high because, well, you get tired, you sweat, and blah, blah. It's like an enormously small fraction of the mass energy. If you have one particle, a proton, and you move it by accelerating it, let's say in the beginning, the mass energy is still way higher than the movement energy. Now, at the LHC, because particles go to such high energy, it's the opposite. The movement energy of the proton is 7,000 times its mass energy. That's ridiculous. That's extremely high. So what happens when you collide the 2 protons? Protons are gone, you mix, blah, blah, and you have an energy which is equal to 14,000 times the mass of a proton. So now the energy, random parts of the energy will be used to create new particles. So you take a chunk of the energy to get the mass of the particle to create particles, blah, blah, and then all the energy that is left is randomly distributed to give them movement. That's how it works. And so the absolute upper limit of these 14,000 proton units of energy, so we have all this energy, you could make 14,000 protons from it, but they would not move because all the energy is finished now. So again, try to understand. You're not breaking open the proton and see what's inside. No, you're destroying it. You get a soup of energy available, and then you make stuff from it. I hope that answers the question a bit.
Yes, I think there are many other questions, so you will have to work after the talk, but I think that you can go for the wrap up just in a couple of minutes, describing the future of what you presented.
Okay, so I will quickly go here then. So what now? We found the Higgs, what now? What is the things? Well, first things first, we expand the search. Of course, we are still working with LHC, but one step forward is making bigger machines, because bigger, larger, better, basic philosophy. So we are developing, this is more like a study, could we potentially build a bigger machine? It's called the FCC, Future Circular Collider. And so this is the LHC, 27 kilometer. FCC will be 80 kilometers or 100. They're not sure yet which of the two options. And they're actually studying here around the region, where would it fit? Would it be possible in the ground? How much would it cost? What would it need? Blah, blah, blah. So we have a case study that is finished. We have a project. Now it's a matter of finding money, of course. This will be quite an expensive machine. This is not decided yet. This would be for 2035, 2040, so long-term planning. Personally, I'm not sure if it would be worth the investment. I think so, because we need to go to higher energy. We need to explore, but it will be very expensive. So it's a matter of, this is no longer physics, this is politics. But that's, let's say, expanding the search on the experimental part. Why would we do that? Well, because we have things in the theory we don't understand. One of the things, for example, is the antimatter asymmetry. What is the antimatter asymmetry? Well, you see, the whole universe is made of matter, normal matter. There's no antimatter. And I told you, well, these two are actually the same thing. Well, where is all the antimatter then? If they're the same thing, why don't we have as much matter and antimatter? And in fact, if you do the calculation, if you measure around the universe, this is cosmology, and you see, well, this scale here, 1, is all the amount of matter in the universe. So this is one universe. At the Big Bang, we had 10 billion amounts of antimatter and 10 billion plus 1 amounts of matter. The 10 billions annihilated and the 1 matter is left today. Why? Why this asymmetry? Why not exactly the same or totally different? Why this very small difference? We don't like that. So there are a few explanations possible. We don't know. We're looking for it. Another thing that is on the open to-do list is dark matter. We see there should be something more in, for example, rotation curves of galaxies. You see them turning. You see how much mass they have. Why? Because, well, what you see is the suns, the stars. And we know that all the mass of a solar system is inside the star. Also in our case, the mass of the planet, you can just ignore it as compared to the mass of the whole system. So you can look, the mass of the sun is, the star is the mass of the system, and you know how much mass a star has by how much light it says. And from this, you can calculate how fast it should turn, rotation curves, and it should change in function of the distance. So this is the turning velocity, and this is the distance, and it should be like that. What we measure, however, is it doesn't stop, it doesn't go down. And this means that well, the only way to explain it, there is more matter here than we can see. So there is dark matter that does not give light, but we don't know what it is. Different explications, like are there black holes? We don't see black holes. Weakly interactive massive particles, there are neutrinos. Or does gravity maybe behave different on big scales? We know now already black holes cannot be. Does it behave differently? This is my personal favorite. I think this might be actually explication. But anyway, keep on looking, keep on explaining. Same with dark energy. You probably have heard this before. This is the whole thing the universe is made of. Stars, 0.5% of everything, because we have then free gases, then we have dark matter, way more than normal matter, and then we have dark energy, even more. Open questions, explications for that. Again, these are all theories, very difficult to prove, but we look for small hints that one of them may be right or not. So then, before I stop, one more tiny thing. Our amazing plot, the one I absolutely love, it has one thing which I did not mention yet. It's this thing. Well, what's that? Well, this is the hope that maybe one day people will be able to find that everything is built from one particle. Instead of all these things, everything, there is only one fundamental particle. That would be very elegant and nice, right? So could this be, for example, string theory? Where the string theory says that everything is built from a string, and vibrations of the string create the different type of particles and stuff. Would it be string theory? Nah, I don't think so. I'm not really a fan of string theory for several reasons, which we can discuss whenever. These are open questions to be left explored. This is actually the main thing we don't know. Exploration is very needed. So we have the two things which define the future of particle physics. We have theory, where we need creative minds to give possible solutions. And we have experiment, where we need big machines to look for hints that a certain theory might be right or wrong. So that was the end of my presentation. So I guess we're actually over time, maybe for questions, but feel free to send me an email. I am very slow in responding, but I will try at least to be nice.
Many thanks, Fred. I think that we should almost stop the lecture here, because we have another lecture in a few minutes. But really, I think that you clarify a lot of points, and we will send you many other not so easy questions that students asked. Some are really require some deep trip in our knowledge, but I think that you will be able, with your time, to answer all. So thanks, and thanks to all the students, and hope you will receive soon the answers to your interesting questions prepared by Fred.
Thank you as well, and thank you for giving me this opportunity to talk, and thanks for all the students to have made it to the end. It was a lot of info, but
yeah, thanks to the jest, but they will make it. Okay, thank you. Bye, Fred.
Bye.